my name is Hayley, and today we're going to be looking at solar electricity, how we can produce it, how we can construct a model out of it, and then the educational value for students across all stages. So just a heads up, I am looking at my screen here for the slides. So if I look away from the screen, you do know why. So, first of all, what is electricity? So we know there are two types of electricity. We have static and current electricity, which will be our main focus for today. So current electricity is produced by active electrons that generate what we call a current of electrical energy. These electrical currents can then be represented in diagrams of various circuits. For example, we look at figure 3. This is called a simple circuit, but how do we know this is a simple circuit? So let's go to figure 1. We can see there are realistic objects here and their circuit symbol, which is what we use in science to draw these diagrams of what that object is. So for example, you've got the battery in figure 1. We can see how that is a circuit symbol in figure 2. So with this knowledge, we can then analyze our diagrams properly. We can see that we have a battery, a light bulb, a switch, and some wires. So we can tell this is a simple circuit because it has one electrical component or resistor, aka the light bulb. It has a battery, which is our voltage source, and the wires which conduct the electrical energy. However, there is this switch, but that isn't an electrical component because it doesn't convert any electrical energy, which is why this is a simple circuit, because it only has one each of the components. It's very minimal. We also have two other types of circuits, and they are series and parallel. But how can we tell the difference between them? So, a series circuit contains two or more resistors along one path, whereas parallel circuit has two or more resistors along multiple pathways. So let's look at series first. As seen in figure 4, we can see our two light bulbs along one pathway connected to the one battery. By looking at the video, we can then see how the current flows through this circuit, which raises the problem: what happens when one light bulb doesn't work? The other one can't work. So these can be seen in everyday items such as Christmas lights. If one bulb along that string of lights doesn't work, then the other bulbs will not work either. However, if we go back and look at figure 5 at the parallel circuit, we can see how this problem is avoided. We can see that we have a light bulb connected to its own circuit, but then connected to this is another light bulb, which is why it's called parallel circuit. So by looking at the video, we can see how the current flows through this and avoids this problem, because if one bulb stops working, the other bulb can continue to function. We use this kind of circuit in, for example, everyday households, because if one light stops working in one bedroom, the rest of the house will not be affected. The lights can still stay on. Furthermore, this allowed me to explore combination circuits of series and parallel from one energy source, as seen in figure 6. Further implications on this topic will then be discussed when looking at the construction of my model, but this video does display how the current may flow through a combination circuit, which also led me to inquiring whether a 1.5 volt energy source, does it power a combination circuit? We don't know, we'll explore that later on in this video. So this led me to asking the question, how can one form of energy transform into another? This can be found in everyday examples such as a microphone that converts sound energy into electrical energy, or a toaster that converts electrical energy into heat energy. However, I was most intrigued by the concept of transforming light energy into electrical energy. This concept is commonly known as solar power, which can be explained by looking at figure 7. We can see how the sun radiance is absorbed by what we call a solar panel, which converts the light energy into electrical energy conducted through the wires to light up the light bulb. This has many advantages, such as it is good for the environment because we are using the sun as a renewable energy source. However, there are many disadvantages, such as it being weather dependent and expensive. To further explore how light energy is converted into electrical energy, I decided to construct a model on solar power. Firstly, I needed these materials, which I tried to reduce, reuse and recycle as many materials as possible. However, I did need to go to Jaycar to buy the solar panel, the motor and the wires, which only cost $14 anyway, which is still cost effective. So moving on to my scientific inquiry, I found this quote from the science rationale in the Science K-10 syllabus, and I found it really connected with my learning journey I went through making this model, and I thought it would best represent it to show you how I trialled, tested and refined my ideas towards solar power. Firstly, I had a few concerns that the 1.5 volt solar panel would not power the 3 volt motor. However, I was successful when trialling the solar panel when connected to the motor and exposed to light energy. Although, this later posed problems when testing the power of the motor. Initially, we had successfully constructed a working solar boat from recyclable materials. However, when placed in the pool, the motor was not strong enough to propel through the water. As you can see here, when we lift it, it works fine, but when we put it in the water, it stops working. Therefore, I refined this idea and reposed it as a ceiling fan to model how solar energy powers everyday households. So here you can see I used my recyclable materials to make a house. To stick the ceiling fan at the top, and the solar panel then sat on the roof, which I also found accurately represents how it's applied in everyday life. My solar power model, which I'm very proud to say was a working model which exceeded my own expectations. On the left here you can see an image of the final product, and on the right you can see a collage of images of me creating the product. So let's have a look at the video to see how this ended up functioning. So as you can see here, the solar panel is on top of the roof. And when we put that down and expose it to the light energy, the motor starts moving. Yay! You can see the wires are at the back. I wanted them hidden just so it's more aesthetically pleasing. I used recycled resources to decorate the inside of the house as well. So, when I put my hand over the panel, we can see it stops because I'm interrupting the energy. If we go a little bit, it slows it down, but then if I take my hand off completely, it speeds it up. So we can see how we can control it through the light exposed to the solar panel. So making this model allowed me to make a few future implications, such as how could I integrate a combination circuit into this diagram. So, as seen in figure 8, you can see that I only really used a simple circuit because I had one resistor, the motor, one power source, the solar panel, and wiring. So, how could we make this combination circuit? If we go into the video, we can see here that on the outside I've added another component of the light bulb with the motor to make this a series circuit. I've also put in a switch so then when the household member turns on the switch, they will get light and the fan working at the same time. So then, the parallel circuit. I've added in a second light bulb with a switch and a buzzer with a switch. The buzzer's there as a doorbell, which I thought would be pretty cool. However, I've put in this second light bulb in the instance that for some reason if the series circuit on the outside doesn't work, they will still have light from the parallel circuit. Except they won't have a fan, so they'll just have to put up with the heat. So, this also led me to asking the question, what happens with the 1.5 volt solar panel? How will this affect the circuit? So if we were to apply this to a combination circuit, I predicted that it may slow it down, things won't be as strong. So when we look at the video of the model of the current, we can clearly see that the series circuit has a weaker current, which means the motor may not spin as fast and the light bulb may not be as bright. However, in the parallel circuit, we can see it's slightly faster than the outside, which means that light bulb and that buzzer will work a bit stronger. So to solve this problem, we could up the volts, which will be shown in the video, which allows it to work a bit faster. So if we were to do this with the solar panel, this would mean providing more panels so then more light energy can be absorbed to convert into more volts. However, we don't want too many volts because if we do that, it may explode the bulbs or overwork the motor, which will just mean nothing will work at all. Constructing these models provides multiple educational opportunities across all stages. However, more specifically, by investigating how electricity can be used in a product or system, 3 outcomes from the physical world strand can be explored by Stage 3 Year 5 students. So, outcome ST3, Stage 3, 8PW, Physical World, ST, Science and Technology, states that a student can explain how energy is transformed from one form to another. So, a student develops knowledge and understanding of the natural world as they explore how solar panels transform light energy into electrical energy. Additionally, this allows them to look at cross-curriculum priorities such as sustainability as they investigate renewable energy sources, how they're good for the environment, and also reduce, reuse, recycle materials in constructing their models. The next outcome we have ST3, 3DP, which stands for Design and Production, T, Technology. Students are able to work on the objective of skills as they plan and use materials, tools, and equipment to develop solutions for a need or opportunity. More specifically, students can sustainably produce and implement their products when testing and evaluating their ideas and predictions. More importantly, they learn to value the importance and contribution of science as they collaboratively seek solutions. Here we come to outcome ST3, 1WS, working scientifically, S, science. So, opportunities to achieve this can be done through inquiry-based learning. So, by having students plan and conduct scientific investigations to answer testable questions and collect and summarize data to communicate conclusions, they become immersed in their learning journey, which also allows them to gain a deeper knowledge about the content. So, how can we do this? Students first pose the inquiry question, which is, how does electricity used in products or systems? Which further allows them to predict, plan, and conduct their experiments. Furthermore, the concluded data can then be compared to their prior predictions, which allows them to gain a deeper meaning and knowledge of the content they've just learned. Furthermore, this allows them to gain a value and attitude towards science as reflective, informed citizens. Various concepts from other key learning areas can be integrated into this as a science lesson. For instance, as students understand and accurately represent circuit symbols within their diagrams, they are actually using concepts from the Mathematics K-10 syllabus within statistics and probability. Furthermore, as students comprehend informative language and texts when engaging with procedures to produce these models, they are also showing achievements from the English K-10 syllabus. And finally, as students show the creative and visual art skills when constructing 3D forms from recycled materials, they are also showing that they can do these outcomes from that KLA. Well, I'm glad I could share this learning journey with you. I hope you learned something because I definitely did, and this has definitely evolved my teaching pedagogy for future practices in science. So, a series circuit contains of 2 or more components within
electronic circuit is made up